This lesson is a summary of the 20-lesson calculus. This lesson is also accessible in the set of 16th lessons on mathematized thinking. This is acting as a binder for the longest set of lessons, that is on calculus. If you have already experienced this lesson earlier, you may skip it. This story of calculus is what I call as the mathematized calculus, and that is how it is presented ahead. Simple can be harder than complex. You have to work hard to get your thinking clean to make it simple, but it's worth it in the end because once you get there, you can move mountains. Who else but Steve Jobs on the power of thinking simple? Mathematics helps us compact and simplify quantification, and calculus does that supremely well. For the real mathematics is not in numbers, but in inventing the thread that assembles certain numbers together. Calculus created a whole new way of threading instant values of continuously changing situations. Calculus took mathematics to the next level of simplification of the complex. Calculus is the most significant catalyst in the development of modern science, technology, and engineering. Because it is the language to quantify continuous change, whether in surface shapes, quantities, or relationships. To that extent, it is a means of seeing the world and expressing what we see, all this to derive new quantitative understanding. Recall, every language has its own vocabulary, grammar, etc., in a way that it enriches what we see and say. Thus, broadly speaking, mathematized thinking is akin to acquiring another language capability, and it is mathematized thinking that sets the pioneering scientists, technologists, and engineers apart. At its core, it is powered by the ability to visualize objects and situations and verbalize the visuals in specific words. For example, theoretical physicists, also called mathematical physicists, conduct most complex experiments in their mind and then verse it in most precise words. No wonder physics sees a fair share of theoretical physicists who get their theories right to the last detail. Mathematized calculus is my phrase. It is my way of isolating the appreciation of calculus that is rooted in visualization and verbalization of the real world. It is back to basics, literally trusting just our eyes and using 8th grade mathematics to explore all that 8th grade mathematics fails to duly explain. Calculus simply fills a gap in mathematics, and the gap that is real, an integral part of our lives. So, why wait to revisit why we use calculus and how we use calculus? The first reality check: the length of curves is beyond the 8th grade geometry. One kink in an otherwise straight line, and whatever we know about measuring lengths fails. All area and volume formulas fail to apply to even slightly curved surfaces. Indeed, the formulas for the area of circle, the surface area, and volume of cones, spheres, and cylinders are derived using calculus. And the education system keeps us so clued out of this fact. Obviously, it should not be hard to realize that most things around us require calculus to find their length, area, and volume. Pertinently, we also know by sheer logic that we can see curved lines as a series of very small straight lines, mathematically called infinitesimal lengths. And if we can measure those small lengths and add them together, we can get the length of the curved lines. The second reality check: many quantities that cannot be measured directly but are integral to our lives. Speed, for example, is a derived quantity. It is derived from distance and time. Similar is the story of electric current and the economic concept of marginal cost of producing something. Marginal cost is not directly measured. It is the rate at which the total cost of production of something changes with respect to a change in the quantity of production of that thing. Thus, marginal cost of something is derived from its total cost function and the quantity of output produced. The third reality check: many changing quantities actually reflect changes in something else. Perhaps the simplest example is grade 6th physics, how acceleration varies with varying force. Such relationships are mathematically captured in calculus. But how do we miss learning this? We are taught force equals mass into constant acceleration. We learn this relationship as discrete, not continuous. That is, for a given force, there is a given amount of acceleration, rather than understanding how a change in force changes acceleration. Science is proven knowledge of nature, technologies build on science, and engineering physicalizes technologies. The three extensively use equations involving changing quantities. The same is true for economics, finance, and other social sciences too. Such equations are called differential equations, a part of calculus. Let us recall that continuous change is the common thread across curves, derived quantities, and equations with varying variables, not x and y, but changing x and y, for instance. To be clear, continuous change in something does not mean variation at all moments. It simply means change of some kind. Is the nature, reality, certainty for that thing, over small or large time period, due to itself or due to change, is something else. We will explore motion to investigate the basic nature of continuous change. Motion is a very composite, multi-dimensional example of continuous change. Time of travel, distance traveled, speed at any instant, direction, acceleration, all change during motion. So how do we define a change like motion, which involves many dimensions that can change? The truth is, the change in motion cannot be quantified or fully described by one quantity alone sized, or stated in one quantity. For instance, even time and distance together, the two things we directly measure in motion, are very short on fully describing any motion. Yes, there is much more to motion than time and distance. For example, there is really little of an option about knowing speed, direction, and acceleration of a motion. And there is more beyond these three also. To top it all, speed and acceleration are not directly measurable quantities. We have to derive or compute them from the measurable primary quantities time and distance. The grade A8 mathematics defines speed of motion as average speed, calculated by dividing the total distance traveled by the total time of travel. Similarly, acceleration is defined as average acceleration, calculated by subtracting the initial velocity from the final velocity and dividing by the time taken. To be mathematically precise, the average speed is actually an average rate, or averaged way of finding rate. Speed is a rate, a ratio relationship of how distance changes with time. Acceleration is also a rate, a ration relationship of how speed and direction change with time. Average is the other name for statistical mean of many values. Long story short, average is the one value for all the values. Thus, in the context of speed, stating average speed is to offer one value of speed for whatever the values of speed may be in the motion. Materially, this gives speed and acceleration just one value each for an entire motion. But assigning one value to speed and acceleration for longer periods cannot be farther from truth. In most real situations, speed and acceleration continuously vary back and forth. It is this factualness of continuous change that the idea of calculus resolves, helps us compute the actual varying speed and acceleration. Sadly, up to secondary education, the story of motion is presented in a half-truth form, emphasizing constant average speed and acceleration over a long period of time. This only exacerbates the appreciation of change and the measure of change, which is calculus in the higher grades. Indeed, continuously changing quantities can only be measured in continuous way in a series of instants. Speed and acceleration are best seen as changing, with their values appropriate and accurate for small periods of time. Heartily, the idea of instant measure of rate of something that is continuously changing is obvious, even intuitive. In those instants, which are very small periods of time, the quantities being measured can realistically be assumed to be constant. Mathematically, it means no averaging of values. The one value is the only value. The measurement becomes a truthful reflection of the condition of the quantity. For instance, instant value of speed, computed from the distance traveled in a very minute time, can be assumed to be constant in that time. That is, it would be fair to assume that any attempt to slow or fasten speed would not show impact in such small time. And how do we measure quantities over an instant? The same way we measure them over longer periods. Mathematically, rate is the only way to compute how something changes with respect to another thing. Rate is the ratio of final minus initial quantity divided by the corresponding period of initial to final quantity. For example, measuring the value of speed at an instant is the distance traveled in that instant, the difference between the final and initial positions divided by the period of the instant. Expectedly, rate of change of something is how we derive certain quantities. Speed is the rate of change of distance over time, and acceleration the rate of change of speed and direction over time. Distance and time are primary, physically measurable quantities, while speed and acceleration derived physically non-measurable quantities out of the primary quantities. Thus, speed is called the derivative of distance over time, and acceleration the derivative of speed and direction. The table shows a few other quantities, primary and derived. Power is the derivative of energy or work. The rate of change of work over time is power. Force acting on a body at any instant is the rate of change of momentum of the body at that instant. Indeed, the big deal about differentiation in calculus is finding derived quantities from primary quantities. That derivation is the rate of change of something. Thus, derivative is the rate of change. And because all this is due to things that continuously change, the rate of change is found in instants. There is another way to appreciate derived quantities or derivatives. The rate of change of some quantities has a valuable meaning, and it can be used as a distinct quantity. The rate of change of velocity tells us more about a motion, and we use this quantity and call it acceleration. Thus, derivatives have a physical meaning, use, and importance. By default, derived quantities may also change in a way that their rate of change is a meaningful quantity. Acceleration is the derivative of a derivative. It is a derivative of velocity over time, which is the derivative of distance over time. More generally, second derivatives are widely used, and you certainly know more of them, of course without realizing they are second derivatives. Third derivatives, fourth derivatives, and beyond are also possible for some quantities, as long as the derivatives have some useful purpose. For instance, jerk is actually the derivative of acceleration, and automobile engineers computed to define limits of acceleration so that acceleration is not too fast. Hopefully, the story of calculus so far was a breeze, just all logical and real world. The idea of rate or ratio average was the only mathematical tool needed, and that is grade 8th mathematics at best. It should be unsurprising that there are quantities that are derived by doing the opposite of how we get derivative quantities. These antiderivatives are called integrals in calculus. Their idea is as simple. Concisely, let us revisit what we do to get derivatives. We slice up the period into a series of instants to get instant values rather than average value. Thus, antiderivatives consider a period as opposed to instants and get the average value as opposed to instant values of quantities. For example, the antiderivative or integration of acceleration is the average velocity or speed and direction over a period of time. Why the name integration? Because it integrates instants to give a quantity value over a period. And one more detail, it may be obvious that the rate of change is also at the core of integration, not just differentiation. Indeed, calculus is about rate of change. Derivatives and integrals are the two pillars of calculus. Congratulations. Conceptually, there isn't more to derivatives and integrals than what you've already learned. However, the world of change quantified by calculus often appears in equations, not just standalone quantities. To the point, imagine an equation, x plus rate of change of y with respect to time is equal to 20. Here it is not the variable y, but it is s rate of change with respect to time that is important. Such dynamic equations are reflection of the real world is. These kind of equations are called differential equations as they have derivatives embedded in them. To solve them, we use integration. We are familiar with how to solve x plus y causes something kinds equations mathematically. Expectedly, differential equations are solved to get another equation, better called function, of the kind we are familiar with, that is, without the derivative terms. For example, the cooling of a cup of coffee can be described by a differential equation where the rate of change of the coffee's temperature is proportional to the difference between its current temperature and the ambient temperature. Solving this differential equation through integration gives us a formula we can use to predict the temperature of the coffee at any given time, based on the initial and ambient temperatures. Believe it or not, we are now just one entity away from comprehensive conceptual clarity on school calculus, which is practically the calculus most of us need to know. To get there, we need to understand what gets differentiated or integrated. In other words, how do we mathematically capture and express continuously changing quantities? Expectedly, we cannot avoid the fundamental tools for stating relationships in mathematics: equations, algebra, and trigonometry. Simply stated, at the end of it all, calculus is a conceptual and method innovation that builds on algebraic equations and trigonometric equations to express continuous change. Broadly, the two calculus operations, differentiation and integration, work on equations expressed as functions. This form of functions is a fundamental concept in mathematics that relates variables. For example, x squared plus 5 equal to 0 is an equation, but y equal to x plus 5 is a function because for any change in x, the input, y, the output changes. The picture shows the compound interest function, which relates the compound interest amount to an equation that computes the interest. The graph illustrates how the compound interest amount changes with changing interest rates. The graph also shows that it is a continuous function. Even the smallest change in rate, principal or tenure of loan affects the compound interest. A function f is said to be continuous if, for the most part, small changes in the input result in small changes in the output. Recall, the rate of change of a quantity is central to both differentiation and integration. Since calculus works on functions, we have to discover a way to find the rate of change of functions. But the rate of change of a function at any instant is the slope of the tangent at the point of interest, that is, the value of the variable on the graph of the function. This knowledge of slope is a 10th grade geometry, no higher. The picture shows a curve, the graph of a function, and also shows the tangents at various values of the variable. What is relevant in the graph is that the slope of the tangent lines varies along the length of the curve. Thus, to know the slope of the function, we have to compute the slope of the tangent at each point. Drawing and measuring the slope of tangents is a very tedious task, and not an effective solution for determining the slope of the curve at any point. Interestingly, our story of calculus hits a snag here for the first time. No prior knowledge can help us find the slope of a given curve without resorting to drawing a tangent and then finding its slope. The idea of limit was a breakthrough in calculus. It was a new foundation and concept introduced for resolving the issue of finding the slope of a function without relying on tangents and their slopes. Interestingly, we are face to face with limit and continuity at the very end of our story of calculus. And you may register that we are ending the story of calculus at limit and continuity. The reverse is true for most school textbooks and classroom teaching, leading to a widespread confusion. Though that is a story for another time. And the idea of limit is very simple. In a way, had to be, the complex situations have simple solutions. What limits allow us to do is examine such a small segment of the curve of a function, that the curve. Please hold your breath and listen ahead. If an infinitesimally small curve segment overlaps with the tangent, then the value of the slope of the tangent at that point becomes the value of the slope function of the curve at that point. Most importantly, the slope function of the curve remains consistent, although its values change along the curve, but its values different over the curve. Congratulations! Now there are just two conditions for ensuring the validity of a limit, and if those hold, then the slope function of the curve true for the entire curve. First, the considered infinitesimal part of the curve must be infinitesimal enough to be a straight line for all kinds of functions and their curves. This is a matter of mathematical accuracy. The second condition is a new concept in itself, because it is about the function itself and is kind of visible in its curve. If there is a lack of continuity in the curve at the point of tangent, then the numerical value of the function, that is, value of the curve before the point, will not match the value of the curve after the point. In such cases, the slope function or the slope equation will not be the same for the entire curve. Thus, continuity is the other essential condition for the slope to be valid for the function. The consistency of the rate of change of a function is considered higher if at two instants around the chosen instant, both before and after, the computed values of the rate are the same as the rate value at the chosen instant. This is all there is to the foundation of calculus. Conceptually, idea of limit is old. Greeks had the method of exhaustion. But the idea of continuity is far assertive concept in modern mathematics, quite newer. And the final word, actually an advice to student learners. Here it is: being equation or function dominated, practice is key to solving calculus questions. Typically, very high familiarity with algebraic and trigonometric simplification and identities. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.